hear you. We can hear you.
Okay, I'm sending this message back 19 hours through time. In the next 12 hours, scientists are going to unearth a tomb in Egypt. So whatever you do, do not open it, okay? Just kidding. I'm in New Zealand. I had the option of going to Houston, but you know, I'm in New Zealand, in Rotorua for the IAFC 2023 volcanology meeting. So I'm sorry I'm not there with you, but thank you to folks running this. Thank you for Tibor, who's going to get his, is going to earn his pay now with all the clicking he's going to do for this talk. I'm going to present to you a high-level overview of a mission concept that we've been working on for more than a year called Phantom, a Venus Aerobot mission. So next slide, please. So Phantom is a multi-platform mission concept that we've been developing for a New Frontiers class mission. So something approaching $900 million phases A through D. I think a lot of you know that it's no secret we've been working on this for New Frontiers 5. NASA seems to have made a decision that they are not going to reverse to exclude the Vice team from the New Frontiers 5 competition, in which case we're going to continue developing this concept for NF6. Thank you to those in the community and those in the room and listening who've contributed to our letters and our emails to NASA to ask them to reconsider that decision. But we're targeting 8 New Frontiers competitions, the kind of scale of mission this needs to be. And Phantom comprises 2 elements. So next click. The aerobot itself, a variable altitude aerial robot. This is a CG rendering of the thing here on the right. It is a variable altitude balloon. There is a superpressure balloon inside that's what gives this thing its peanut-like shape. There is a zero pressure envelope around it, and by exchanging helium gas between the 2 reservoirs, the balloon can change its buoyancy and thus change its altitude. So nominally, it'll traverse a range of 52 to 62 kilometers. It will operate for more than 30 days, potentially quite a bit longer. That's still something we're working on. And it'll nominally carry a payload, a gondola, that's about 100 kilos, of which about 20 will be a science instrumentation. Click. Thank you, Dior. The Aerobot is accompanied by a science payload-equipped orbiter, which does 3 things. It provides data relay for the Aerobot. It tracks the position of the Aerobot. It will probably be in an inclined eccentric orbit with either a 24 or 12-hour period. That's something we're working through. It'll also provide context data for the orbiter, for the Aerobot itself, which I'll elaborate in a few minutes. Next. So the overall mission theme for Phantom is volatiles at Venus. I know you're going to have a Venus volatiles panel discussion later, which unfortunately I'll miss because I'm going to go back and convene the other session I'm doing here at IFC. But I think a lot of us recognize that volatiles are the key to understanding Venus. And it encompasses multiple cross-cutting science questions. A lot of this informed by the new planetary decadal origins, worlds, and life. So some of those questions include the chemical and physical properties and processes of terrestrial planet atmospheres, how atmospheres of rocky worlds are lost to space, and in fact, how they are replenished and made in the first place through the release of volatiles from rocky mantles, the history of volatiles in the geophysical and geochemical evolution of terrestrial planets. It's a pretty wide-ranging thing, including things like plate tectonics on Earth, and the role of volatiles in developing and maintaining habitable environments, and particularly for some of our evolutionary models for Venus, even killing habitable environments on a large rocky world. This concept of volatiles centers Venus at the middle of a bunch of cross-cutting questions that are underpinned and defined by the new 2023-2032 decadal survey, OWL, Origins, Worlds, and Life. And as Tibor will show in the next click, Venus is a singular destination for asking these questions generally. So I know it may sound a little trite, but I don't conceive Phantom as a Venus mission. It's a mission to help us understand the role of volatiles in the evolution and formation of large rocky worlds generally. Venus happens to be the place we go to tackle these kinds of questions. Next. So this is a very brief primer on the history of aerial exploration of Venus. Venus is one of the few locations in the solar system other than Earth, Mars, and Titan where it is possible to have a long duration heavier than air vehicle fly through the atmosphere. The pathfinder for this was the Vega 1 and 2 balloons flown by the Soviet Union in 1985. They operated for 2 Earth days, close to 44 hours. They had no altitude control. They were carried with the wind horizontally and vertically. They had a modestly sized balloon, about 3.5 meters across, and a very small scientific gondola, but they demonstrated a bit like Sojourner on Mars that you can successfully float a science instrumented payload at Venus. We have the next one now is going to be Da Vinci. Da Vinci is going to be groundbreaking in terms of what it's going to tell us. However, in the area where we anticipate phantom operating, it's only going to spend a few short minutes there. It won't have altitude control to traverse or to govern how long it's going to be there. It won't make cloud measurements. It is going to give us key noble gas isotopes. They are going to be at one location at one time. They are going to be extremely important, but they're not going to be, by design, going to give us the atmospheric data we might want from Phantom. Whereas Phantom, the next, we'd argue, natural step in the process of exploring the atmosphere of Venus from inside the atmosphere will operate for more than 30 days, between 52 and 62 kilometers. It'll have active altitude control. We anticipate by passively being carried by the wind, it will circumnavigate Venus in between 5 and 7 days, depending on its latitude. We will take science measurements at all different times of day, at all longitudes, a wide range of latitudes and altitudes. Right now, the baseline design is a 14-meter wide balloon carrying 100 kilograms of the gondola. It'll characterize the full chemical inventory of the atmosphere, including aerosols. We'll get information on 3D atmospheric dynamics. We will do seismic and remnant magnetism investigations, and we will also, as I'll describe further in a moment, start to characterize the interaction of the ionosphere with the solar, wind, and the space environment. I want to just make it clear here, and I think I'll illustrate this to you in a moment. None of this is designed to say that Vega or Da Vinci aren't important or aren't critical to our understanding of Venus. But I want to emphasize to everyone listening here, including those of you who may not know that much about the history of Venus exploration, that no 1, 2, 3, or even 5 missions is going to answer all the questions we have. These missions are complementary and they build upon one another. So what you're seeing on this, this blank slide here with a bunch of words, these are the kinds of things that if you went back in time, like I'm doing with you, a few decades, and you asked people, what would you want to know about Venus, either in terms of science questions or data, this might be the kind of list you come up with. It's not designed to be exhaustive. It's designed to be illustrative of the kinds of things that you might want to know about Venus. So if you click once, let's say in situ surface composition, well, we have this. We have this in Venera. Now we have extremely limited information from a handful of places, very large error bars, not much more beyond major element chemistry of the oxides. But we have something. So we have a rough idea that, you know, it's not made of cheese. Next. Thanks to Venus Express, we've gained a sense of what the atmosphere is doing remotely. That was extremely helpful. It's not in the atmosphere, but it is still good for giving us a synoptic overview of what's happening in the atmosphere. Next. Thanks to Magellan, we have global radar coverage. Now, I think any of us who use Magellan data routinely know that those global data are helpful, but they are not nearly enough. I'd argue right now that with the data we have from Magellan, we have something comparable to what we had with Viking for Mars. Enough to get a sense of the broad picture, but not really enough to really get into the hard questions. Next. And we have the proof of concept Aerobot, thanks to Vega in the 1980s. Next. Now, thanks to Akatsuki, we have long duration cloud remote sensing. And that's been important to understand the dynamics building on Venus Express measurements. Again, it's remotely sensed, but it is an important mission. And it's good that we still have right now an active orbiter at Venus. Next. As the new missions come on stream, Veritas is going to give us global radar data. It's going to help us look for surface change detection. Now, Veritas will do other things too. This graphic I'm showing you is simply to kind of highlight some of the big things that these missions are going to give us. It's not designed to be exhaustive, but we're going to be able to compare like with like, surface features taken with Magellan, taken with Veritas, and even over successive cycles in the Veritas mission to see if we can look for evidence of change in the surface. Next. We're going to get noble gas abundances. We're going to get other measurements too, including, and I cannot tell you enough how excited I am to get aerial photos of Alpha Reggio, but we're going to get some really important information about the Venus atmosphere from the Da Vinci probe. Next. And with Envision, we're going to get global surface composition, as well as high resolution radar for select areas of interest and subsurface radar sounding. I mean, I cannot wait for the Envision mission. But again, these missions still leave a lot of these important science questions unaddressed because Venus is an extremely complex system and there's a lot more we have yet to answer. Next. That's where Phantom comes in, because with the Aerobot, we're going to be able to explore cloud layer habitability. Next. We'll be able to explore mesoscale processes in the atmosphere by looking at what the Aerobot is doing. Next. We'll be able to look at aerosols for the first time, working out what the inventory of aerosols is in the middle atmosphere, different latitudes and longitudes, and different altitudes to understand what we're seeing. Next.
About 3 minutes.
Cool. By searching for crustal remnants, we'll be able to determine information about the crustal properties, and by listening for volcanic infrasound, which is one of the reasons I'm here at IAVSI, because there's a growing, vibrant volcano seismoacoustic community here, we can begin to listen for the heartbeat of the planet itself. Next. Radiative balance, by looking at how radiation is transferred from the top to the bottom and vice versa, we'll be able to start getting information about what the energy budget in the atmosphere is, which will help us move toward understanding superrotation. And then with the magnetometer, which is going to be baseline both for the aerobot and the orbiter, we're going to search for that remnants, the crustal remnants, because we found remnants on the Moon, Mars, and Mercury. So is it on Venus? If not, what does that tell us about the interior? And we're also going to be able to characterize what the ionosphere is doing in reaction to the solar wind, both from within the atmosphere and from orbit. In fact, if you look at the orbiter by doing long-term synoptic observations of the atmosphere in the spirit of what Akatsuki and Venus Express has done, we'll be able to get more information on the exchange of momentum between the solid body of the atmosphere to work toward our understanding of atmospheric superrotation. And for the first time, the orbiter will also be equipped, next, with a set of instrumentation to essentially be Vaven, to characterize atmospheric loss, escape mechanisms and species, and relate that to what we're learning from within the atmosphere itself with the aerobot. Now, if you click again, you'll see there's still a lot of really important stuff: long duration surface science, mineralogy, petrology, surface atmosphere interactions, in situ seismicity, geochronology. And again, this is not an exhaustive list. This is to show you that even the Phantom mission with its aerobot and orbiter will not answer all of these questions. And so we need decades of Venus, and I hope to emphasize that to all of you listening. But we are positioned to take a serious step forward with this New Frontiers class mission. So if you click one more time, I'll leave with you simply an illustration of the kinds of things that this mission is going to help us answer by being inside the clouds of Venus itself. That's the presentation. Thank you very much.